Hey everybody, welcome back to Opti201. This presentation is on hidden gems of optimization, which are things that shouldn't be overlooked when you're developing an optimization model and solving them, because they can really improve performance, speed, and solution quality, and a whole bunch of good things to make your problem just easier and faster to solve. So let's hop into the agenda. So what we're first going to talk about are ways that we can improve performance via understanding MIP gap and variable starts or warm starts. We're then going to talk about handling competing objectives, so multi-objective optimization. Then we're going to look into handling multiple scenarios, what if analysis, and things that you can change between scenarios. And then how we can gather multiple solutions. So let's hop into improving performance. To understand how to improve performance, let's get some reminders from Opti101. So when a mathematical optimization model completes successfully, the solution that you get is guaranteed to have two characteristics. One, the solution is guaranteed to be feasible given your constraints. And two, your solution is guaranteed to be globally optimal. And other methods really can't guarantee this, so definitely a big strength of mathematical optimization. We also found that LPs are typically pretty easy to solve, particularly for powerful solvers like Gurobi. By and large, linear programs are pretty quick solves. But we found that mixed integer programs can be difficult to solve. While understanding, the size of the problem in terms of the number of variables and constraints definitely is a little bit of a factor. Other things like the structure of the problem definitely are important in understanding how long it may take to solve. So we saw that solving a MIP involves solving multiple LPs, possibly exponentially many. And a common method that we described was called branch and bound. There are other things that Gurobi uses and other solvers use in addition to, but this is one that's sort of easy to explain to sort of help you understand what's going on. I'm going to give a very quick little rundown of branch and bound. So it starts with relaxing a MIP into an LP. So again, getting rid of the integrality constraints, but everything else is exactly the same. Then it's about branching, which you find a decision variable that should be integer but isn't, so something that's like 3.5. You add a couple new constraints, so say you add a constraint that says y must be less than or equal to 3. That gives you a new LP. And then y must be greater than or equal to 4, and then that's another LP, and you continue to solve. Looking at these LPs and how they sort of progress will help you determine upper and lower bounds on an overall optimal objective value. And this will also help you prune branches that cannot improve the objective value. So because MIPS can take a long time to solve depending on a lot of things, it's important to find ways to balance speed and also quality of solution. So is it worth, being a few percentage points off of optimal if you get your solution super fast? Maybe, maybe not. It depends on the problem and what your goals are. But we're going to talk about a couple ways to help understand the speed and quality sort of balance. One is MIP Gap, which provides a measure of how far a current solution is from optimal, potentially from optimal. And then also talk about warm starts, which give a MIP hopefully a good place to start its solve. So now let's dive into defining MIP gap for maximization problems. So let's say you have a mixed integer program and I hand you an integer solution. And an integer solution is something that has all the integer values where they need to be and also satisfies all the other constraints. That's going to provide a lower bound on an overall optimal objective value. Let's denote that current best solution by ZSOL. And now let's also take a quiz. And before we get into this quiz, a couple things. One, find the polling feature in the Hua web app or mobile app. And also take a quick look at this picture on the right because that may help you. All right, so our quiz time question. Suppose we have a maximization problem. The optimal objective value for a MIP will always be blank when compared to its relaxation. Greater than or equal, less than or equal, always exactly equal, or you cannot know for sure. I'll give you a few seconds to think about it, and then we'll continue on. A few more seconds to find the polling area and to submit your answer. Okay, so if we think about the relationship between a MIP and its relaxation, its LP relaxation, there are more options in the LP than the MIP, and everything that is in the MIP is also in the LP. So because of that relationship, the answer to this question is B, less than or equal, because the MIP is more restrictive, meaning the optimal solution for the MIP is also going to be in the LP, so that solution could be optimal, but there are a bunch of other points that the LP has that the MIP doesn't, so maybe one of those points provides a better objective value. So I hope you enjoyed the quiz. So now, talking about branch and bound again a little bit, when we was going through that process, we were talking about how you select a variable and then you add more constraints. When you add more constraints and produce more LPs, those are called sub LPs. And as you keep going and branching and bounding and all this sort of stuff, you go down these trees of LPs. The sub LPs become more restrictive because you keep adding more and more constraints. So because you're adding more and more constraints, you're getting less and less options. So it's sort of the same idea that we're just talking about. So because of that, the objective values will tend to decrease. They definitely won't increase though. So let's denote the greatest of these these LP objectives, so all these upper bounds, among active branches by Z bound. So that means MIP gap is defined as Z bound minus Z sol, the absolute value of that, divided by the absolute value of Z sol. So it is the relative difference between Z sol, your current best solution, and Z bound, which is the largest of your upper bounds among active branches. So if the current best solution is suboptimal, so we're not quite there yet, or we don't know that it is optimal because maybe we got that solution, but we have more branches to explore. This provides an upper bound on how far the solution that we have now can be from optimal. So if this MIP gap is, say, like 0.05, that means that we are no more than 5% away from optimal, which is a nice thing to know. And it also provides a useful stopping criteria for what could be good enough for our problem. So that's how MIP gap can help you understand where solutions are relative to potential optimal, and how it can provide a stopping criteria that says, okay, maybe we're good enough and the solution that we have is fine. Let's move on. Speaking of moving on, let's move on to variable starts, aka warm starts. And what a warm start is, it's a way to take advantage of previous solutions, maybe model insight or subject matter expertise to improve performance. So to understand what this is, let's just run through a quick example. So let's say that we built a 6-month plan for a planning application. So 6 months, and we have some optimal plan that works here. So from January through June, we know we have an optimal solution for something. Now, let's consider 1 month later, we're going to rerun our optimization model. So it's starting from February, running through July. Well, from February to June in solution 1, we have some overlap, and what happens in February through June may be a good starting point for February through June for the second run. Just seems reasonable, particularly if not much has changed in maybe input data or something along those lines. So specifying something like this can really improve where the solver starts, and um, and then make it much more easier to get to your global optimal solution. So to sort of see what it looks like in our Python API, let's again talk about another quick little example where we're opening and closing plants. And so let's say that we wanted to um, provide a warm start where we first open up all plants. So we set we set the plant open, our decision variable open to 1, and then we decide to close the one with the highest fixed cost. So then that'll eliminate one possibility, because it seems that maybe from intuition or from experience that the plant with the highest cost is always closed. So that may be one way to use some subject matter expertise to help speed up a solve. So now let's head over to handling competing objectives. It's often the case that real-world optimization problems have multiple competing objectives. So if you think about shipping, you may be a shipping company that obviously would want to maximize your profit, but also minimize your late orders. And you can see how those two things may be conflicting. You may also want to minimize shift count while maximizing worker satisfaction. Minimizing costs of production, but also maximizing product durability. And then from a portfolio view, you want to maximize profit while also minimizing risk. So this is a lot of, I'd like to have my cake and eat it too. Often these objectives, when you go in one direction, you're sacrificing something. And you go in the other direction, you're sacrificing something else. So it's all about maybe finding that balance point. So when we have competing objectives like this, how does Gurobi handle these trade-offs? Well, let's consider a problem from Opti201, the second modeling example. In that problem, we wanted to minimize electricity purchased through the grid utilizing solar panels and batteries. But we also specified a second objective. Given expected prices, we wanted to minimize the total cost of electricity purchased. And then through some exercises, we added constraints around battery's depth of discharge to consider battery health. So when do we know that something like battery health should be maybe another part of it, another objective, or should it be a constraint? So if we define battery health as the number of time periods a battery is below a certain depth of discharge, we can define a decision variable VBT, where B is the index over our batteries, T is the index over our time periods. That's going to equal 1 if and only if battery is below a certain depth. So far we have a set of current objectives. We can potentially choose to minimize electricity purchase costs or purchase amount. And then we have some constraints. We have all of our constraints that we had in the problem. Then we also have this battery health one, if we want to consider it there. And if we consider it a constraint, then that means that we can set an upper bound for the number of times that each individual battery goes below this certain depth of discharge. So it's a hard constraint that must be satisfied. But maybe that may not be what we're looking for exactly. We could also consider battery health to be an objective itself, and considering that solely. So we may want to minimize the number of times that we have a battery go below this depth of discharge. But that may not be inclusive enough because we're not considering all the purchase costs and purchase amounts. So we may actually just say, hey, let's consider all three of these as part of our objective. And that's what multi-objective optimization is all about. So once we decided whether something should be part of the objective or a constraint, we have a couple options. And yes, I did hop my camera off a little bit for this one, just so this slide's going to be action-packed, so I didn't want to get in the way. Don't worry, you'll see my face again soon. So one option is what we call a weighted multi-objective, in which you optimize a weighted combination of the individual objectives. So we have our purchase costs, we have our purchase amount, and we have our battery health sort of indicator. Essentially what weighted multi-objective is it just adds those objectives together. And here's an algebraic form for it, all scaled by some weighting. So what's great about this approach is it is very simple to implement. If your original problem was a quick solve, this isn't going to add any extra complexity there. But where it gets a little bit complicated is, sometimes minor weight changes can lead to significant solution changes, particularly if you have a lot of integer or binary variables. Sometimes small weight changes can have big solution changes. And also, how do you value the occurrence of your battery going below its depth of discharge compared to a kilowatt hour of electricity purchased, and comparing that to a dollar amount of electricity purchased? That's a little bit of an abstract concept to really have a solid grasp on. The other method is lexicographical, sorry, I always mess that up a little bit, or hierarchical. And these, in this approach, you optimize each of these objectives in a priority order. And every time you sort of go to a different objective of lower priority, you limit the degradation of the higher priorities from its objective function value. So let's go through that, and this will make a little bit more sense. So let's say that our highest priority objective is purchase cost. So we solve this mathematical optimization problem, and we look at the objective function value at where we have our optimal point, and let's call that Z1 star. Now let's move on to the purchase amount. So we have a new objective, which is the purchase amount, all of our original constraints, but then we add a new constraint. And that new constraint is the purchase cost must be less than or equal to the optimal value that we found in the first one, plus we're allowing some room for degradation. Again, since this is a minimization problem, we're trying to push it down as much as possible, so we're allowing it to increase a little bit, or maybe a lot of it, it all depends on the problem, but we're allowing it to increase or degrade. And then we consider battery health. So we, again, want to minimize some objective with respect to battery health, again, subject to all of our original constraints. And then we have two constraints, the F1 as before, and then same thing for F2. So it's our purchase amount, but we're allowing that to degrade by some other tolerance. And so what's great about this approach is it does something that's that we were talking about before, is you can speed up some of the computation here, some of the solve time, by using the Gurobi specific functionality here, because you could, if you wanted to, just set up these individual optimization models and just run this in sequence and actually sort of code all of this up. But by using Gurobi's functionality here, you allow for warm starts from one problem to the next. So going from problem 1 to problem 2, it makes sense to use the optimal value for your decision variables going from problem 1 to problem 2. So there's a nice warm start there. And the same thing from problem 2 to problem 3. So let's use those values, those variable values, to really speed up the solution time. And that's what happens when you use the multi-objective functionality within Gurobi. Let's move on to handling multiple scenarios. So what if analysis and seeing what we can change between scenarios and some tips and tricks to do this. So one of the consistent things that I found, particularly in my experience in consulting, is every project or most projects always included something about what if analysis and what if planning. And that's a definite real world project management problem that is there all of the time. And it's very real because there are very real concerns that people have when solving problems. So maybe someone's going to ask you, well, what if shipping costs change, or what if the options that we have to ship change? What if we need to make budget cuts, significant budget cuts, really significant budget cuts? On the other side of that, what if we can show what's possible with additional budget? Maybe there's a lot of ROI by giving a small increase in the budget. What if potential production locations aren't approved in time? So there's some legal battles happening, or paperwork or something like that, where it may be possible that we want to open a production facility in a certain city, but it just may not be approved in time, and we may need to consider other options. And also, like, what if proposed like environmental regulations are passed? That's going to change how we need to do business, and we need to be prepared for that. So all of these things you should be prepared for, and sort of leadership on project teams will want these answers. Well, you can answer these types of questions by changing a few simple things. The objective function coefficients, variable lower and upper bounds, and also constraint right-hand sides. And just by changing these things, you can help answer all of these questions for individual problems. So how does handling multiple scenarios look in our Python API? Well, let's say that you have a base model, so some mathematical optimization model, the good old, if you're familiar with this, C transpose X, subject to AX equal to B, X between its lower and upper bounds. So we have a base model that can be any single objective model handled by Gurobi. We can specify some known number of scenarios. Let's say it's 3. And in scenario number 0, we change the linear objective coefficients. In scenario number 1, we change some variable bounds. And in scenario 2, we change some constraints right-hand side. That's easy enough to do just by using the syntax that you sort of see here. And then when you optimize the model, Gurobi works on solving all these scenarios simultaneously. So it's not just, hey, I'm going to run scenario 0, solve it, start over. Scenario 1, solve it, start over. Scenario 2, solve it, start over. There's actually a lot happening in the back end that I really can't even begin to describe. But there are very, very smart things that are happening so that you're getting all of the goodness from scenarios working together and Gurobi solving it all sort of simultaneously. And then when you want to query the results, then you just specify a couple parameters, and boom, there you go. You can extract these solutions for individual scenarios and see how they compare. So the last topic that we're going to talk about for this presentation, for this session, is gathering multiple solutions, this is something that I am really excited to talk about, even though we only have a few more minutes in this session, but I really like this capability. So when you talk about optimization, there's this idea that there can be only one solution. There's only one optimal solution. And whenever I think about that or hear about that, I think about the wonderful movie Highlander from 1986. But when you sort of think about it in a more, modern context, is sometimes you don't know what your priorities may be for problem solving until you sort of see them presented in front of you. So here we have this example of using Google Maps, and you sort of see going from one velvet taco to another, that you have a few options in front of you, and each of these options have some pros and cons. You have on the right with the yellow times, those are shorter distances, or excuse me, larger distances but shorter times. And then on the left in the gray, you have a longer time but a shorter distance. So what are your priorities? You may not even know that you have them until you sort of see what they are. So yeah, having only one optimal solution, one route, or one plan of action can seem pretty stressful. So it may be a good idea to optimize, but bring in some really close friends of that optimal solution. So, and this is maybe important because some preferences, you may not even know what they are, or they may not even be quantifiable. And you may want to compare alternatives to the optimal solution and sort of see, hey, if I let this slip a little bit, what does that even open up for me? And this also gives a greater feeling of control, which is something that I described in an earlier session as a hindrance for some people to adopt optimization, is that it's again, sort of black boxes to some people, and if you're the one who's in charge of decision making, having that feeling of control is important. And then this may help also identify any missing model elements, some things that you may want to restrict. We sort of described this in one of the earlier sessions when we talked about the widget problem, and one of the shipment values was 2. That identified something to us that we may want to implement into the model, and looking at a large sort of swath of solutions may also do that. So to do this and to analyze a bunch of different solutions, what we do is we define a solution pool. And this helps us report multiple solutions automatically, efficiently after a single run. And there's a couple of different ways to go about it, and we're going to dive into those in a second. But I do want to note that there are some subtleties and limitations here. With continuous variables, multiple equivalent solutions won't be reported per the way this is all set up. But now let's dive into how we can extract some of these multiple solutions and what that really means. So what's our menu for doing that? So what can we mess with when defining our solution pool in order to get some different behaviors to sort of fit the need that we have for getting these extra solutions? So if you set your pool search mode to 0, there's no additional searching that happens. You just sort of go through the optimization as normal, and you hang on to every solution that you come across. Again, think about branch and bound. You get solutions that are integers. You're just going to hang on to all of those, but you're not going to do anything fancy to find more. When your pool search mode is 1, and your pool solutions is n, you're going to store n-1 additional solutions. So it's a specific number. And when you have pool search mode is 2, solutions pool is n, and your pool gap is x, what's going to happen is you're going to store n-1 n-1 best solutions that are all within a MIP gap of a certain percentage. So this is pretty specific, and this is going to require exploring the search tree more, exploring more nodes, doing more branches and bounds. So how do we implement this in our Python API? Pretty straightforward. Pool solutions 100, pool gap 10%, with a pool search mode of 2, just by updating some set parameters. So that is all that I have in store for this session. Hope you learned something cool, at least maybe a bunch of cool things. But the next thing that we're going to do is we are going to implement some of this fun stuff in a hands-on modeling exercises part 2. All right, I'll see you there.